with a history that includes working on Formula One, America's Cup yachts, satellites, implanted medical and veterinary devices, he's definitely in the know. To give us the lowdown on advanced manufacturing, please welcome from the University of Sydney, their Chief Engineer of the Sydney Manufacturing Hub, Bruce McLean. Give it up for Bruce. Yeah. Woo.
Hi folks, how are we doing? My name's Bruce McLean. I'm the Chief Engineer from the Sydney Manufacturing Hub, and our mission is to deliver advanced manufacturing solutions to the research community. So we're part of the university, but we're not part of any particular faculty, so we say we're faculty agnostic. So we service all comers from all disciplines and all directions. What I'm going to talk to you today about 20 minutes, it's a fairly high-level presentation. So just overarching trends, what's going on out there in the advanced world, scale, power, speed, economics, a little bit about data analytics, and then some of the future solutions and what's on the horizon, beam energy technology, solid state technology, materials and multi-materials, and then a little bit about what happens after that. So the current landscape looks a bit like this. The top left there we have Next Flex, which is a United States defense initiative. That's a flexible polymer with a 3D printed electrical circuit on it, embedded electronics, it's got an antenna on it. It could be stuck to a soldier to give GPS and positional and temporal information. That exists, it's in the field now. In the center there's a typical volute component for a space turbopump rocket engine application. That shows a couple of things. It shows the surface finish is quite good. It's a merchantable part, it's got minimal support on it, it's very well designed, very, very little post-processing to do to get that into a real-world part. Top right there, the little cruciform, that's actually a close-up view of a mesh structure, and it shows at a scale about 0.5 millimeter across the truss. We can build that in quite some detail with powder bed fusion. The manifold there, the old days we used to machine them out of billets and blocks and drill holes in them, only to the extent where we could get a drill or a tool path. Nowadays we make them with, in this case, binder jet in 316 stainless steel with an optimized flow internally for minimum pressure drop, minimum weight, maximum performance. Kind of hiding in the middle there's small circles. Those are actually living things. Those are stem cells. So we're bioprinting. We're actually taking stem cells and we're growing stuff. Just think about that for a minute. So think about organs, think about soft tissue, think about neural material, and it is all going on. The topologically optimized structure there is a bit of a fanciful rendition, but it shows just what's possible. So optimized for purpose, for structure. It's an organic looking shape. It can be built, it is being built. Bottom left is a Prusa. They have a stand here. Great little platform. That's actually a hot-rodded Prusa. You can buy a kit on the aftermarket to turn that into a 4D printer. So you can print it sideways. It's a few $100, you add it onto the Prusa and off you go. In my mind, that means the technology's arrived. The aftermarket's attacking it now with customization and accessories to what is already a very useful device. The maxillofacial implant there is quite typical of what's going on in the biomedical space. Trauma reconstruction, bone cancer repair. That one's a particularly interesting case. That's from South America, from a colleague of mine in Sao Paulo in Brazil. And you can see the small video clip circulating there is the first metal printer in space. That's sitting on the International Space Station right now, producing things. It went up there in January. Some might call it a DED welder, some might call it a plasma, some might call it beam energy because it's working in a vacuum. If you take a look at the cabinet on the lower right there, it kind of reminds me of a replicator from Star Trek. So we're kind of on the way there. There's some conjecture in the market right now amongst the commentators. Some of the American commentators and some of the European commentators disagree on the health of the industry. That's an interesting discussion in itself, but the upper chart shows quite a dip in laser powder bed printer sales in Europe in the 2023 time zone. whereas the American source report underneath it shows 744 more printers were sold in 23 than 22. So who do you believe, question mark? So on the one hand, it's industrial metal printers, on the other, it's pretty much all industrial printers. So there's some noise in the data there, so be careful what conclusions you draw. So today, everything's about scale, right? So everybody's listening to the media about what's going on in the defense community. We're talking AUKUS, we're talking land vehicles, we're talking maritime, we're talking aircraft. It's all about forgings and castings and replacements. So that's a seriously large casting, Sheffield in England in the top photograph, a forging, excuse me, and a seriously large crucible melt pour going on for a casting in the bottom one. How do we get from that, from traditional manufacturing technique to advanced and additive, question mark? If we're serious about supporting the Starship type scale, to build the real Starship type scale in space, we need forgings and castings on the scale of the left of the view there. We haven't actually got there yet. So you look at the Starship leaving the Earth, it's got 33 individual engines on it, and they're all running together. What we're going to try and do is maximize the reuse of that vehicle by bringing it back, servicing it, and sending it up again 1 to 10 to 100 times, whatever we can get to. Wouldn't it be smart if we could build, let's say, 3 engines or maybe 4 engines instead of 33 engines and still lift the same payload? Think about all the pumps, valves, supply, plumbing, fuel delivery, steering, and navigational equipment to support 33 engines simultaneously. So there's an engineer for scale there standing in the middle of a build envelope of an actual machine built by a custom house for electro-optical systems in Germany. That's their current largest printer. It's 800 by 800 by 1.2 meters high. And it's been built specifically to make rocket engines in one piece. But that's about as big as it gets. So the lower right is the current Ariane 6, the lower and the upper stage engines. They are on the right order for the upper section without the nozzle on the bottom. The 4 copper parts in the middle there are from a relatively space vehicle called the Terran 1. That was the first launch of additively manufactured GR COP 42 engines that I'm aware of. The traditional engines in the middle of the view there are what we're up against. So the engineer for scale in the build box is another engineer for scale standing adjacent to the nozzle. See the obvious difference in scale. So we've still got a ways to go there yet. The upper right is direct energy deposition, so wire arc or laser arc deposition. That's Relativity again, US company. They're making their propellant vessels additively. The last rocket they launched was substantially additive from top to bottom. So that's about where we are today in the scale side of things. On the opposite end of the spectrum, we've got small. So resin printing technologies, electro-deposition technologies, so-called 2-photon interference. These are a stupidly small scale. If you can think in nanometers, you're doing better than me, but some of the stuff here is picometers. So right in the middle there's an example of a horizontal feature that's less than 150 nanometers across. So that's 1/10 of a micron. So if you're measuring with a micrometer, a micron's pretty small, but that's 1/10. Now, the current state of the art says 150 microns actually easy, so now they're going to drop the standard to 100 nanometers. So the company in the middle there, Nanoscribe, their Eiffel Tower is 1 centimeter high. The company on the right, Up Nano, they can put a lady with a handbag with a croissant to scale on the observation deck of that Eiffel Tower. So just to give you an idea of how small that is. So things are getting very small. Helical spring, 10 microns diameter. It's metal. Upper right, those are micro needles, so they're for drug delivery purposes. Again, on the order of 100 microns diameter there. So there's 10 companies listed there. I'll draw your attention to one of them, Scienta. They're a local Australian startup. They spun out of university. They've come from ANU in Canberra. They've now set up in the Cicada Innovation Precinct here in Sydney. So watch this space. I think they've got a very interesting technology. Their IACS conductivity with copper is excellent. It's 80% of IACS standard. Most of the other 3D printed electronics out there are lucky to get to 20%. So that immediately means it's more efficient, they can package it smaller, and so on. Okay, power. So it's all about power now, right? So if you know anything about laser technology, everybody's building bigger lasers, more of them, and bigger and bigger. So it's all about more power. However, the more power you start to put into a fixed volume, the heat management challenges start to magnify. So you've got gross heat in and you've got to get gross heat out. You've also got thermal management as far as the microstructure. So you've got more traverses of the beam across the microstructure, the solidified microstructure. So you're going to mess with it a lot more than you would in the old days when you just had one laser beam. Energy, obviously, is a function of how many kilowatts you put in. So the more power you put in, the more kilowatts you put in, the more it costs. We've got issues with multi-lasers, multiple laser generators. If you start with 10 identical laser generators and turn them all on day one, by day 10, one of those or two of those are going to have deteriorated more than the other 8. So you've got this issue of unpredictable deterioration in the laser quality and the focal plane and the drift in the laser. So you've got to pack them in as well. You've got to deliver the laser beam and you've got to steer it. So today we're still using mechanical means of steering mirrors, galvos or vario scans. You get to a point of saturation where for a given build volume you can't fit any more lasers in, so it becomes challenging practically. All the sputter and soot and gas flow management issues are magnified by the number of lasers going on, and as is the control system software complexity. So it's easy when you're doing a solo. This is a concerto now. We've got a whole orchestra playing together, interacting and behaving in concert to achieve the build. So run down the right-hand side. So you have a bigger beam, you typically have a bigger beam spot, which gives us a bigger heat affected zone. We've got an increase in scan track spacing, so we've got a bigger beam spot so we can pitch the scan tracks further apart, which is a good thing. However, that gives us a step over problem when we go to the layer thickness. We can use bigger particle powder diameter because we've got more power to melt it, so that's good because it makes it cheaper. It also makes the build quicker because we can get away with a thicker layer. And finally, just to talk about the wavelength of the lasers we're typically using. Most folks here are familiar with the sort of near-infrared continuous wave lasers. They're running at about 1 micron, 10, 20 nanometers, 10, 25 nanometers. If you take a look at the absorption chart, sorry, it's a little bit poor quality in the middle there. If we're trying to melt copper with a laser beam, a near-infrared laser is almost useless. It's only able to transfer about 5% of its energy. We'd be far better off using a green or a blue laser, which is exactly what Trumpf and a couple of other companies, New Brew and Enlight, for example, with blue laser solutions. So for the same power, we could transfer 65% more efficient than we could with a near-infrared laser. So choose the right laser for the right application and the right material. Some folks are working with pulsed and multiplex lasers. That's more in the small scale stuff, but it is getting some attention in the larger community as well. It's not for everybody. And then the final thing I'll say is just when you've got lots of power going on, you've got switching, right? So you've got to switch stuff on and off, skywriting and so on. And the more and more lasers, the more and more switching you've got, the more and more failure opportunities that generates. You can see on the lower left, there's another volute housing. I just chose this one to illustrate something about the usefulness of a more powerful laser system. So Velo in California are servicing the new space industry pretty heavily. This is Haynes 282, which is a really interesting material. It's crack prone, it's really difficult to weld, but with a really powerful set of lasers and a bit of cleverness with preheating, not only can you produce something useful with it, we can produce it with minimal support. So that, as you see there, allegedly, is how it was made. No support. I'm a little skeptical, but that's what the claim is. The rocket engine assembly there is a demo part from Nikon SLM Solutions. Photographed that at Formnext in Germany last year. And talking about just the sheer scale, when you can see another engineer for scale there, standing beside the qualification coupons. So if you're going to qualify this thing, you need to print coupons the whole height of the build, all over the build plate, hundreds and hundreds of 4-inch coupons. So to actually qualify the process to take advantage of the power and the build volume is really complex and really challenging. The relationship between volumetric energy density is pretty well known by most folks in this community. So if we crank the power up and don't touch anything else, we can very easily find ourselves outside the optimum processing window. So if we crank the power up, we have to actually scan the laser faster, or we have to increase the hatch distance, or we have to increase the layer thickness to keep the VED result in this optimum solution space. Speed, everybody wants it faster and faster. Yeah, good idea. Volumetric energy density mentioned again there. The Ishikawa diagram, none of my presentations are complete without one of these, so you have to look at a whole lot of interrelated factors. And speed features in the middle of that swarm there. I'm not going to go through it. What you can see on the left is an interesting photograph from a Chinese company called Bright Laser Technologies. They have a machine that has 20 lasers simultaneously operating. You can see they're building small parts, but they're building a lot of them. So that's actually one way of doing it, is to multiply the laser quantity in the build volume, but still build small parts. The other way, of course, is just to move the beam quicker. BLT, certified, airworthy on Airbus airplanes. They're making turbine parts that are flying on Airbus airplanes right now. So we've got to steer the beam and we've got to focus the beam, and it's fairly much a mechanical process, so there's hysteresis and things can only move at a certain speed. I'm an EBM guy. We do it with magnetic steering coils, and we've got like 3 orders of magnitude faster than that, so we're pretty happy. However, technology is moving on with EB as well. In the bottom right, you can see traditional line melting, so that's a shot through the X-ray grid in the viewing window. On the left, you can see a line scan, so the hatching is being done in a strip manner, traversing. What you can see on the right is essentially spot welding. So the steering coils are actually that flexible and versatile that we can actually have the beam touching down simultaneously. Today, it's 64 at once. Very soon, it'll be 128 at once. It's only a single beam, but we can control it where it puts the energy very, very effectively and very quickly. So it is another way of getting speed out of the equation. The other obvious one is to forget about the beam and focus on all the other peripheral activities in the machine when the beam is off. The recoding time, any movement, any physical shifts and movement that are going on, and improve the overall efficiency. This one is to stimulate a bit of heckling. There's quite a number of opinions out there about the economics of additive manufacturing, and I have a standard answer for that, and all my staff know this. It depends. It depends what you're talking about and in what context. This is a little article that was setting out to prove just how good binder jetting was relative to laser powder bed fusion. The answer is they're two totally different things, and it's not possible to compare the two of them together. So I would say you're looking at apples and oranges here, and I wouldn't draw too many conclusions from this at all. Binder jet is great if you have a small farm of furnaces out back that you can sinter all the parts in when you're done with the printing. So this graph doesn't even show that, and the cost per part and the time per part doesn't include all the furnace time that's going on out the back. The range there from sort of tens of cc's per hour to hundreds of cc's per hour, that's about where we are at the moment. But speed on its own is not the answer. Building rubbish parts quickly is not going to help anybody. So I always say, think about the value triangle, the usual stuff, quality, cost, time. Yeah, you want to optimize those three depending on the product and the part you're making. No heckling? Okay. Data analytics. This is a really busy field at the moment, and there are many software providers and scanners and imaging providers here today, so go out there and talk amongst them. The workflow, the so-called digital thread, is extensive. And if we look at the sort of current practice, there could be 8 to 10 different softwares involved from the beginning to the end. And wouldn't it be great if we could do all that with one particular product? That would remove a whole lot of file formatting issues. So we've got a basic design, we've got some simulation, we've got some machine preparation, we've got some distortion management, we've got some slicing, then we've got the actual build itself, and then we want to measure it or conform it afterwards to make sure that we got what we thought we were going to get. A lot going on there. A lot of opportunity for sensors, measurement, energy, thermal, chemistry, backscattered radioactivity in the case of electron beam. So there's a bunch of things that can be done. Some of them are currently constrained by the speed of the computers we've got, so we can't get the I/O in and out quick enough to close the loop on the control system. They're working on it, and it's an opportunity for sure. The guy in the bottom corner, it's pretty real. What software do I buy? How many of them do I buy? How much is the subscription? And by the time you've made that decision, there's a new package on the market. So it's a really, really fast-moving field. Richard Feynman, a very notable Nobel laureate, atomic physicist. He's always pushed that you have to work at it. Nothing comes for free. All right. AI is a thing, yes, but it only does what it's taught. All right. So if you teach it rubbish, you'll get rubbish back. I used to love chihuahuas. I used to have one. Tell me how many blueberry muffins there are there versus how many chihuahuas. And that is actually a really good practical illustration of what can go wrong with machine learning. So you've got to give the right instruction set. The top right is a scan from a prior company I worked in. That's a spacecraft component. It's about 300 high. It has 13 tubes. They all converge on a common center point. And that's a structural node for a space frame structure in a geosynchronous satellite, communication satellite, made out of titanium. That deviation overall is inside 20 thousandths of an inch. So we're able to hit that sort of tolerance with a bit of practice in terms of roundness profile. And the point on this slide is that we used structured light scanning to conform the part. Previously, the only way you could measure that was on a coordinate measuring machine, and that would send an average engineer nuts. 50 pages like the Sydney telephone book of XYZ coordinates, and how do you know it's good? This way, you get a visual with a deviation histogram on it, a header, an index, 3 pages of report. Inwards QC is about a 15-minute process. So you've taken a 3-week conformity check to make it less than an hour. Okay. Apologies, I forgot about the bicycle. Some cycling folks have dropped by the stand today. That's my understanding. That one is the Italian Olympic team effort. That's additively manufactured. It's using some pretty exotic materials. Scarm alloy, so a scandium-dosed aluminium alloy. A lot of carbon fiber in that, a lot of aerodynamic smarts, a lot of CFD modeling, super-duper wind tunnel testing. That thing is state-of-the-art. It's not cheap, and I don't know, maybe they'll win the Olympics, maybe they won't. Okay, let's talk about what comes next. Beam energy technologies, where are we going with beam energy? There's a company spun out of MIT by a bunch of their alumni called Surat Technologies. That's an old French philosopher, which is quite an apt name for a company. They have a concept called aerial printing. So they're not rastering a beam around a profile, as we do traditionally or conventionally. They're actually printing in quadrants at a time. So they're multiplexing small diode lasers and actually laying down 50 by 50 millimeters, 50 by 50, 50 by 50, and a whole array of those simultaneous. So what they're looking for is a metal powder bed outcome from a solution that looks a little bit like a vat polymerization resin printer. So they're kind of hybridizing that technology. They're not there yet, they're still at the optical table level, but they're attracting a lot of significant venture capital investment. So watch this space, I think that'll be the next thing. Multi-beams, we've talked enough about that. How many beams, how many is enough? It depends. Can they build the same part faster? Well, maybe. What about if we focused one beam really finely and concentrated on the contouring of the part to make that look beautiful, and defocused one and had a big, heavy hit to hatch the interior that the exterior surface finish doesn't matter quickly. So we split up the responsibilities of the beam in the same process. Multiplexing the beams. Powder bed fusion we talked about a lot. Bigger, higher power. Get rid of the redundant cycles. There's a company out west called Aurora Labs. They have an interesting technology where they have a slotted recoder. So they're actually lasing in the recoder while it's actually moving, which is pretty cool. Renishaw do that as well. They're lasing in front and behind the recoder because the recoder's depositing the material from the center of the recoder. So they're actually minimizing the redundant steps. The E-beam guys have done the same thing. They've actually reduced the number of discrete steps in the non-beam on time, and they've actually decreased the layer time by something like 25%. The lower right shows a plan view, point net melted tungsten. So think about that for a minute. That's a 3,000 centigrade melting point refractory material. It's absolutely beautiful. You can see the individual segments there where the individual points are simultaneously touched down and translated one point at a time over the surface. The SLM solution machine down the bottom left is probably the biggest one I've seen in person. That only has 12 1 kilowatt lasers in it. 600, 600. It's all closed loop, powder recycling is all done inside the box. Horrendously expensive. Okay, let's move on to direct energy deposition now. So most of these are wire-based. It can equally be powder-based. It can be an arc, electrical arc. It can be a laser beam, or it could be an electron beam. There's a couple of credits missing off this. They didn't make it to the final one, but the stirring component on the top left is 316 stainless. That's a couple of tons, that part. The undercarriage piece in the middle there is actually made by Norsk Titanium for General Atomics. That's a drone on the order of the Reapers that you see on TV circulating around the neighbourhood. GKN, that's a rear spar component, titanium, and there's one identical to that built on the other side of the fixture. So we do that in this technology to minimise distortion. So build one on one side, flip it over, build the other, and it nets off. The top right-hand view there, Norsk Titanium again, that to my knowledge is the first FAA certified flying component in a commercial airliner. That's holding up the galley in a 787 Dreamliner. So there's a few of those brackets in there, and they make them like that. So you can see the blank, you can see the finished machined article. A couple of other exemplars there, titanium material, and in the lower right, that's an Inconel material, again from our Formnext show a year or so ago. What you get out of that picture is scale. What you don't necessarily get out of that picture is the propensity for distortion. So we have this challenge of managing the part evolution and managing the thermal distortion, managing the shrink cracking, managing the changes. So back to the monitoring systems, the imaging systems, the measurement systems, and we're not far away from closed loop control. So we can figure out a process going off nominal, and we can actually make a correction on the fly, so that when we get to the end, we've actually got the product that we intended. Solid state technologies, another interesting area. University of Sydney, SMH, we've invested in both of these technologies actually. So we have friction stir additive device made by a company called Meld Manufacturing in Christiansburg, Virginia, and a cold spray platform made in Dandenong by Speed 3D. So a local company, very successful. Both of these technologies are interesting for different reasons. Speed can be deployed, it can be put out in the field, it can build parts for armoured vehicles for military purposes, marine applications. There's 10 or 11 of these sitting on the border of Ukraine right now in Poland, making parts for armoured vehicles. That's an operational fielded system. The Meld system, the gentleman standing on the left there in that big open area is occupying the space for the test coupon to qualify that machine. The US Army intending to build chassis for an M1 Abrams tank in one piece. So the so-called single piece hull project. You can see a rotor tension member there in the middle that's been excised from a melded block. That's actually flying on an AH-64 Apache helicopter, so it's actually well proven. Conventional IC engine cylinder block made with Meld. In the lower left, won a technical competition a couple of years ago at AMW, Additive Manufacturing User Group. That's actually a hatch for a Bradley fighting vehicle, and that's fit for purpose. That could be put on that machine and run. In the middle, it just shows you the evolution from the blank to the finished part. So you put it on, but you also have to subtract it. So that's when we get on to start talking now about hybrid machines, additive plus subtractive together. Materials, probably the last little bit here, some really exciting opportunities here. For those of you who are aware of metal matrix composites, for example, we make them a certain way. Now we can actually blend the ceramic into the powder at manufacture of the powder. So you can see there aluminium powder with actually ceramic embedded in the powder particle. So that's only on the order of 30 microns diameter. It's full of ceramic already. So we're most of the way there to a hybrid product. In the middle, for the EV community or power electronics or spacecraft thrusters, soft magnetic materials. We've traditionally made them the hard way with laminations, stampings or profile cut and slab them together like the old transformer windings. Now we can 3D print them. We can graduate materials in the same build chamber. Meltio make an interesting machine that's got multi-material capability. It sprays a powder, uses a laser beam to melt it. That block there is nickel bronze and Inconel in each cube, made in one piece. The copper and silver and hybrid in the middle there is cheating a little bit. That's running it out until the copper's over and done with, filling the hopper with silver and carrying on, and then the mix at the end. But it's halfway there. The theory's right. The one in the middle is just outright cheating. That's like running the machine and then taking the plate out of the copper machine and putting it into the aluminium machine and hoping you can get the layers to line up right. If you've got better eyesight than me, you'll see there's some quite big lack of fusion voids in there. So that's not even technically interesting. In the material sciences sense, the university, we have the ability to interrogate microstructures down to the atomic level. So there's a picture of interstitial vanadium in the middle of a titanium matrix. I mean, that's atomic level imagery. In the middle is a paper I saw last year, a thing called a fulgurite, which is a particular quasi-crystalline structure. That was dug out of a sand dune in North Carolina, not far from where the Wright brothers launched, actually, from a lightning strike that hit a power line that mixed the aluminium from the power line and the silica from the sand in the sand dune and made that. Have a look at the structure of it. It's got 12 order symmetry. So if the old days, if we talk about body center cubic, face center cubic, or hexagonal close pack, that's 12 orders of symmetry. Think about the possibilities for strength in a structure like that. So if we could create that and harness it in an artificial manner rather than waiting for a lightning strike to arrive, how good would that be? The rocket engine on the right has copper and nickel interspersed. The top one is a slightly different incarnation of it. The bottom one is done by the Fraunhofer IFAM in Dresden, and that to me is a very good implementation of copper plus structural. So they've got the heat transfer and the thermal properties of the copper and the structural support for the pressure vessel containment of the nickel around the outside printed in one go. The glass printing in the middle, another advertorial for a local company, Maple Glass, excellent idea. Can print borosilicate glass, can print recycled glass. What a great idea. Local company, startup, spun out of university, all power to them. Now what? We've got this fantastic landscape in front of us with material science, but we've also got this consumerism landscape in front of us. So I used to spend a lot of time up in Sheffield in the old days with another job I had. Sheffield has a long and distinguished history in steel making, particularly cutlery. And those scissors there have been around for a long time. 1902 that company started. And they're prized positions for quilters and people who do embroidery and so on. But they were originally for cutting umbilical cords for babies, believe it or not. And that design has been around for so long, it's been plagiarized and copied by everybody. The one underneath there is made out of a stamped product. You can buy it on Temu, $2.65, and I bet it'll be thrown away by the end of the week. The one above there will last for the rest of your life. So I just leave you with that little thought. Wind turbines, I hate the damn things. Look at the blades and look at the recycling challenge we've got there. How are we going to address that on a large scale? These things cycle out through fatigue because they're not perfect. How do we recycle them? If they're made of carbon fiber, how do we do that safely? How do we recycle that? At the moment, we dig a hole and we bury them. I'm not sure that's a great idea. How many bus depots do you go past and there's a big pile of e-bikes where they've been rounded up and thrown in a heap? I mean, that's just another example of it. I just ask you to think about that in the context of what we're doing, especially in the polymer and the composite space. Whilst they're great solutions to structural engineering problems, they're also significantly challenging for the environment. So environmental responsibility, the impact, the decay, the recyclability. That's probably enough pontificating. So I'll leave it at that. And if anybody has any burning questions, we can take them here or catch me later at our stand, opposite corner of the building. So, as I say, it depends. The standard answer for additive manufacturing is it depends. How big is it? How many do you want? Is it dense? Is it porous? What material is it? How long have you got? Yes, but, no, but. And the most important one when it comes to cost or time or complexity is usually pi times the estimate. Okay? Thank you very much.